Okay, please go ahead and start. So we will have a substantial number of presentations, and if there will be not enough time for everyone, then we will roll over to the next meeting. And first will be is something on carbon nanotubes research.
Someone.
No, someone on something.
Okay, yeah, so I guess a lot of you have probably heard a portion of this talk already, so some of it might be a review from previous talks I've given, but so this project is covalently functionalizing carbon nanotubes, more specifically chiral carbon nanotubes. In this work, we're exploring redshifts in defect-dependent charge localization schemes. Wait for the next one. Okay. Okay, so I guess all my equations turn to some Chinese or Japanese, but I guess most of them will probably just be E11 star, so just memorize that.
Well, I guess it doesn't help you. It's a different change.
Okay. Well, can you spell it out, maybe?
I guess it's a homolume gap in the first line, right?
Yeah, homolume gap and E11. If somebody wants to present the PowerPoint and just flip slides for me, that would fix it. But
well, in your PowerPoint, can you hear me?
Yep.
Well, the PowerPoint which I opened from your email, I also have same problem with formulas, except that I don't have Chinese characters, I just have some strange symbols.
Well, that might be a Mac thing then. Is the computer there Windows?
But that computer is Windows computer, that should work. That won't.
You can try, but maybe your main results are not symbols, even if they are correct. But the figures...
Yeah, I think we'd probably be okay, but...
Yeah, I don't think you have these problems on other slides, so we can, I guess, not spend time on this. You just can tell it. You don't need formulas in your outline thing.
Sure.
But you can just say it by words.
Yeah. Okay, so first I'll give some introduction to this work, and some background of what has been already done. Then I'll jump right into the model that we're using and the methodology. And then we'll go into results. So we'll talk about some orientation dependence, the functional group dependence, and then get more into how to analyze these results from a dipole and charge perspective.
But again, dependence what on what?
Oh, okay. Dependence on the band gap and the E11 defect transition.
But it looks good in print.
Okay, so there's been a lot of work done with carbon nanotubes in the past few decades. A lot of the applications, some of them involve drug delivery and telecommunications, so the emission wavelength is very important. Some interesting stuff. So carbon nanotubes are essentially very long, quasi one-dimensional structures, but in reality we can't compute that type of system, so we have to truncate them to some finite length that's been taken to about 10 nanometers or so. But in order to do that, you need a proper capping scheme, which has been shown previously on the left paper that I'm showing. And then other work has been done in the past as well, looking at the optically bright transitions. So in pristine, they're usually dark tubes because the optically bright transition is usually not the lower one. It's usually, say, the fifth one. But also recently, by Yuhuang Wang, published this paper in 2016, molecularly tunable fluorescent quantum dot defects, showed that you can tune these by redshifting them by producing sp3 hybridization defects on the tube lattice. And so that is kind of the starting point from where we'll be going here. So you can see on the left side,
Braden.
Yes, they
Yep.
just here. Yeah.
Braden, I usually just
Yep.
peacefully sleep here, but I have to correct you. You can simulate infinite nanotubes of infinite length and more broadly periodic structures. You just need periodic boundary conditions and Brilliant zone sampling. Okay.
Yes, you are right.
I mean,
But
this is university.
yep. Yep. But we intend to use TDDFT, usually implemented with Gaussian, and Gaussian's not so good with periodic boundary conditions,
Okay. With some
especially
tools.
due to the local basis set and stuff. But
Okay.
so yeah, okay. So it is possible, but in this type of work where we're trying to do finite tubes,
Okay.
to use this other methodology. So yeah, so on the left side you can see Yu Hong also published this paper earlier with sp3 hybridized defects showing where the absorption and emission takes place. And then by functionalization, you can change the lowest optically active transition in these carbon nanotubes. And so that is kind of the starting point and all we need to know to jump right in. So what we're doing is we're using a 10.5 single-walled carbon nanotube. Some parameters there. It's about 10 nanometers long, about a nanometer in diameter, 19-degree chiral angle, about 1,450 atoms, give or take, depending on the functional group. And so, like I said earlier, this hybridization defect, what that means is when you functionalize the surface of the tube, it interacts with the tube carbon and pushes it from kind of a sp2 hybridized to a more sp3 hybridized. So that's why they call it the hybridization defect. So we also explore not only configurations, but different types of these defect groups. So in three kind of main categories, we have alkyl groups, so different lengths of chains from 1, 2, and 6 carbons, either all fluorinated or all not fluorinated. And then we use some aryl groups, just a pure aryl. We have an aryl with 5 fluorines, and then we have the para-bromo benzyl as well. And then we also attempt some direct fluorine attachment and a phosphofluorine group. So you have one defect that you can place in the tube, but in order to have a closed shell system, so close the valence, you need to put a second one on there. So where you put that second one has been found to be of great importance. And so if you look at the 6 nearest neighbor configurations, you have 3 ortho and 3 para. And so we can denote these in 3 different unique directions. So we can call the plus direction, noted in green on the left and top right figures, as being the chiral angle of the tube, or along that direction. And then the plus plus kind of traverses the tube in the circumferential way, and the minus goes opposite almost of the chiral angle. Yeah, and so you can have either one group and itself, or as the middle figure shows, you can have one group and a hydrogen. And the second group we'll refer to as the auxiliary group from here on out. So we use density functional theory, we use CAMB3 loop, which is a long-range correction hybrid functional. We explore some basis sets. We start with a minimal basis set, STO3G, for all the atoms, and then we systematically increase a basis set on the defect atoms. So first we add 631G star on the halide atoms. So in our systems it would be fluoride and bromide only. And then the third type of basis set configuration we have is the entire defect gets 631G star plus the 2 defected lattice or tube atoms that are now sp3 hybridized. And so then we move on. Once we have an optimized structure using that methodology, we can perform time-dependent density functional theory using the best basis set configuration that we've used. And then we perform NTO analysis on the transition states and some NBO analysis on the transition states. So jumping right into the results then, we have the ground state electronic structure can be modified by simply modifying the orientation of these defects. So those 6 nearest neighbor configurations, I have arranged them from least redshifted homolumo gap to most redshifted homolumo gap. So the O plus direction is the ortho configuration along the chiral axis, and the P plus, the para plus, is simply the opposite but going across the ring now in the para position. And so if you look at the basis set, the red line is the alkyl group. So with a change of basis set, we see almost no difference with the non-fluorinated alkyl chain. But then as soon as we go to the fluorinated chains, we see a pretty big difference just giving the fluorines in additional basis functions. But then you see a slight further redshift giving the entire defect plus the 2 tube atoms the added basis functions. And so from here on out, we will use the best one because that gives the clearest redshift per cost. And so now if you look at panel B, we're comparing one group versus 2 groups of either the long chain fluorinated alkyl or the long chain non-fluorinated alkyl. So if you have 1 or 2 chains of just pure alkyl, no fluorines, we see almost no deviation between the groups in their redshift and the ground state electronic structure. But when you do 1 long chain fluorinated group versus 2 long chain fluorinated groups, you see one splits about almost 0.1 electron volts in the most redshifted orientation. And then if you look at panel C, we can compare different lengths of these fluorinated groups. We ignore the non-fluorinated groups because we don't expect the shorter ones or the medium ones to also not to give redshifts.
Braden,
Yep.
On your left or right side with your text, you have in something like you have in the change of the shift around 50 millielectron volts, but on your axis you have maximum there going to 35 millielectron volts. So I'm not sure what exactly you mean by this 50, because definitely your data not corresponds to the 50 millielectron volts of difference. Just because your y-axis is less than 50.
Sorry, those units are in electron volts, right? So 0.35 is 350 millielectron volts.
Oh, so it's okay. Sorry. So it's.
Sorry, I didn't put the units. That's my fault. But is it clear?
Yes.
Okay. So yeah, in C we see significant splitting between the fluorinated chains when you go from 1 carbon to 2 carbons. We see that large splitting. And then when you increase from 2 to 6 carbons, you see a minimal splitting from the 2 carbons, but still quite a bit split from the other groups, the short fluorinated chain. And then in panel D, we explore some of those non-carbon attachments such as fluorine and the phosphorus groups. And here we can see that the 2 fluorine attachments produce an arguably equal amount or more to the long chain fluorinated groups, the 2 long chain fluorinated groups. And then the fluorine attachment in the hydrogen produces one of the lowest. And as we will probably see throughout this entire presentation, anything with a hydrogen usually is very minimally split from the other groups that are also minimally split. And then the phosphorus will actually produce a mediocre redshift in addition to the orientation. So with other groups not carbon with different electron withdrawing abilities, we can get that mid-range gap filled if we would desire. Okay, so then here we can jump right into the electronic structure. Not too much of a different story here. All the trends are exactly the same, of course, for the orientation, because the first transition is mostly comprised of a homolumo transition, so we wouldn't expect the ground state to be much different than the excited state with this respect. But some discrepancies here. In panel B, let me scroll back here. We saw that the C2F5 attachments, so the mid chain or the mid-length chain fluorinated alkyl, was split by almost as much as the long chain fluorinated alkyl groups. But here in panel B, we see that that same C2F5 group is now minimally split from the long chain fluorinated alkyl groups. And this we don't quite fully understand at the moment, but we're examining that. But we see that the two fluorinated groups in panel C is increasingly split from the ground state. And this is intuitive that this should probably be more split because the fluorine is highly electronegative, and it being directly attached to the carbon nanotube would see a very large shift in that charge density onto the fluorine. And so here we can see just a simple absorption plots of some of the most unique orientations, starting from the top on the pristine and the lowest redshifted to the largest redshifted for the two long chain fluorinated groups and the two short chain alkyl groups. And so we see consistently, of course, that the long chain fluorinated groups produces a more redshifted first optically bright absorption peak rather than the short chain alkyl group. And another thing to note is the splitting between the transition energies becomes increased with increasing redshift in orientation. And so we see that there. And then if we compare that same plot to the 2F and the FH system, we see the same thing. And the FH system is actually consistently less split than the short chain alkyl groups. So that further enforces that any group with a hydrogen seems to have a much reduced splitting, no matter what the main group would be.
Before you go, can you again summarize what exactly is the effect? Like, what's the reason why you see the stronger shifts with fluorinated long chains comparing to the non-fluorinated chains? Why two fluorines?
Yeah, so I'll cover that in a couple slides too, but it kind of comes down to the inductive effect, the amount of perturbation to the local electron density there. So the direct fluorine attachment is much stronger than, say, a carbon with some fluorines attached to that, so 2 centers away. So we see that effect directly. But I'll cover that in a bit.
Well, how you explain the difference between just on a single panel, your left panel or right panel, fluorinated alkyls versus non-fluorinated alkyls? But why your non-fluorinated alkyls shifted less comparing to the fluorinated ones? When you
the
have
fluorinated
both
alkyls
chains identical.
Yeah, so if we just consider two identical chains, like on the left panel that I'm showing, the two chains will withdraw electron density due to the electron withdrawing effects of the fluorines onto the alkyl chain, the carbons. But the alkyl groups with non-fluorinated alkyl groups are actually electron donating slightly, and so we'd expect that the localization. So that's my next slide here. The localization is affected by not only orientation but by inductive effects from the groups.
Return back to the previous slide. So your inductive effect over EVA, again, what is the reason? In the previous slides you were showing that if you have hydrogen and one fluorinated group, the effect is not as pronounced comparing to two fluorinated lone alkyl groups. What is the reason for this?
Well, I guess two groups would, I don't want to say double the effect, but would much increase the electron withdrawing effect, and more so the withdrawing of the electron density from the charge as a whole, rather than having a hydrogen there. And that we see that's consistent across all of the groups with a hydrogen. But I mean, that's the main argument, I guess.
Okay.
Is that okay? Yeah. So we can also look at the transition orbitals for those first excited states And so I'm showing the least redshifted on the left side and the most redshifted on the right side. And so you can clearly see a distinction between the two. The least redshifted is very delocalized along the tube. And as we can see either on the next slide or the slide after, those transitions are actually more optically active. Their oscillator strengths are much higher than the ones on the right due to that delocalization of the charge density for this transition. And then you probably can't see by eye, but we expect that the transition density for the 2F and the long chain fluorinated groups to be also slightly more localized than the bottom two. But that's probably not evident by the visual here.
Brayden?
So on this,
There is another question.
Can you go back? What does the percentage mean?
yeah, so, okay, I didn't explain that too. So there's some information in there too. So the S symbols simply mean which transition it is. So on the left side you can see S3, so that means the third transition was the first optically active transition. The other two are mostly dark. And on the right side, for the most redshifted orientation, you see that it's actually the first transition. And so then the second line is the oscillator strength. And then the third line is the amount of contribution of this HODO to the transition.
Okay, got it.
And so here, now we can kind of try to analyze what's causing these results to appear. So if we think about, so I talked earlier a little bit about electron withdrawing effect, which is directly coupled to dipole moment, right? So separation of charge is a dipole effect, or produces a dipole rather. And so you can plot both of the previously mentioned results, so the HOMO-LUMO gap on top and the first transition redshift on the bottom against dipole of each group. And so you can see that there's a nice trend with all the groups, and it becomes more pronounced with increasing dipole around 6. I'd say there's a nice shift toward an intense redshift. So there's some species that deviate in this plot. Notably, on the ground state structure, we have arrow BR. I have an arrow kind of pointing to the uppermost one. All of its orientations seem to be slightly more redshifted than the others. And on the bottom panel, of course, we see that 2F is slightly redshifted, and we understand that because, like I said earlier, the direct attachment to the carbon nanotube produces more intense effects, even though the dipole isn't as strong as, say, the long-chain fluorinated groups. So that raises the question.
Before you go there, it probably also looks like you have much more significant effect of the dipole on a localized states, which are more redshifted, rather than on this delocalized pi-pi delocalized state, which is having almost no shift at all, right? Comparing to
yes, exactly. Yep.
And can you explain this behavior? Why you see that this delocalized state have almost parallel, right? Almost straight line with just a very small curve, while the localized states really showing very significant curve, especially after 6 device.
Well, I'm not sure I can answer it directly, but if the attachments themselves and the orientation that are given produce a delocalized charge density along the tube, the transition will not probably be affected as much due to the delocalization.
But what's the physics behind it? You just rephrase the same thing as observables.
Yeah, I guess I don't know the answer directly to your question.
Well, when you localize electron density, what's that going to do to the dipole?
I think he means if you have particles separated by a longer distance or a shorter distance.
Transition dipole. No. a real dipole.
Looks like you have some kind of discussions there, but
Oh, they can't hear me this time. I'm quiet now.
Yeah, I mean, if somebody else knows the answer, I'd be willing to fold on this.
well, I guess no one knows. So what's happening if you get the answer of the question from the viewer?
We would think about it in much more detail. I would say it's probably just an effect of localizing the electron density. So in the case of the localized species, you're locating electron density near the defect, and the only place where you actually have any perturbation to the pristine tube is at the defect. So that's where the entire dipole originates, right? If you just had a pristine tube, you wouldn't have these dipoles, but because you functionalize the tube, you do have the dipole at the region of, and it's going in the direction of the functional group from the tube. So in the case of the localized electronic structure, you're localizing electrons around the defect, and then, so in that case,
Okay. So overall, you're trying to say that your dipole moment, the tube by itself has very minor dipole moment if it's not functionalized. And the overall dipole moment appears due to the defect. So that's why you kind of clearly see more stronger more stronger effect when your orbital is also just completely localized near the defect rather than when it's spread over the entire thing, over the tube rather than on the defect. Okay, sounds reasonable. What
Correct.
Braden says. Do you agree?
Well, I mean, well, yeah, I mean, the defect is only going to have a large effect if most of the charge density is nearby. If it's far away, it's not going to have as much of an effect. It's essentially the same argument, right?
Yeah. Okay. So we done? You go next, or what? Or something else to say for this?
Yeah. The only thing left in this figure is the sizes of the symbols are scaled by the oscillator strength of that transition, and so you can clearly see, especially on the top panel, the bottom, the delocalized transitions have the most optically intense transition, again, which is because of that delocalization. So, to try and start to answer some of the deviations from these trends, we can look more in depth at the charge. So we can perform an NBO analysis on the aryl groups, because in the previous slide for the ground state structure, we saw that the aryl bromide was further redshifted than the other nearby groups based on the dipole. So
I see your head.
they can't see me anyway. Doesn't
Oh,
matter. But so we performed this charge analysis, and so you can see the odd one out here is actually the fully fluorinated aryl group, as it undergoes that ring charge inversion to give the density to the fluorines. So this really didn't explain why on this plot the aryl bromide showed weird results. So from here we can look at something else. We can look at experimental results.
Can you return back on your previous again this colorful previous
This one?
Next, I mean previous before this. Like you talked about weird trend. Could you probably give a little bit more explanation what is weird about this trend for alleles?
Well, okay, so if
alleles
you
corresponds to this I don't know what color, how you call it, cyan, kind of dark cyan color or tint color, right?
Mm-hmm. Yep.
And
Yeah.
again,
So
if I look on the excited state, it looks like it's not very different from the other ones. If I look on the ground state, then yeah, maybe it's different, but what exactly is weird here?
well, if we're purely looking at the dipole moment to try and get a prediction of how redshifted that species will produce the system's transition to be, or the HOMO-LUMO gap to be, this does not follow the trend of nearly all of the other groups that were explored here. And so
I don't see,
that
what
raises
do
the
you mean it
question as to
doesn't
why.
follow the trend? What exactly not following the trend? Can you
So
point
the
exactly
trend
to
that-
which things do not agree? Again, for the excited state, they completely follow the trend. What's wrong there?
Yeah, just for the ground state arrow BR group. It's further redshifted, higher up than all of them should be if they were to fall near the red line.
But you have it only for the ground state, not for the excited state, right?
Yes, in the
For
excited
the
state,
excited
there's
state, you don't see these deviations. It follows the trend nicely.
yes, it does.
So then I would say, okay, but but again, the ground state,
Okay.
this is not something which you really measured. Like your difference in the band gaps is not really something which is really very exciting to actually
Well,
talk about.
it may not be,
because it's not observable.
but it's still an interesting question that arises. Why is that one different than the other arrow groups? Because they all fall directly in place.
Okay.
So I mean, it's whatever. But then the two F groups, the purple on the bottom panel, that also deviates, and we have an understanding of why that is. So yeah, so on this, I think I talked about this panel. The only deviant here is the arrow F5, which seems to agree in the previous two panels. So this really didn't answer our question as to why arrow BR was going to be the odd one out, so to speak. So then we can kind of take a different approach. We can look at some experimental data, notably Yu Huang Wang's data that he published in the 2016 paper I cited at the beginning, also cited at the bottom here. So we kind of steal his experimental redshifts for that first transition, and then we use his systems. We calculate the dipole and the NBO charge, and we plot them as a function of that redshift. And as you can see, we see really nice trends with these alkyl groups. So the only difference in these alkyl groups is you're changing the distance kind of between the tube and the nearest fluorine on that alkyl chain. So it's essentially along the same series of chemical defects. So it follows a really nice trend.
Is it for 10.5 tube?
These were actually computed using a model system.
But your experimental
methyl-
E11 minus E11 star, which experimental values you're talking about, for which tube? For 10.5?
I'm sorry, this tube was 6.5, I believe.
Okay, so it's a different chirality.
Yes, yep. But we have no reason to believe why this physics would change depending on that for this application. But so then if we extend that from those slightly fluorinated alkyl groups along the same series to a bigger conglomeration of functional groups, as you can see in the center, and on the top right plot, you can see we have the same plot as previous. In black is the dipole moment. Red is the first atom on the functional group's charge, and green is the first tube atom's charge. So you can see the dipole moment is kind of all over the place, especially for the aryl species. Sorry.
Again, it's the same. What's the difference between this and that? This is now 10.5 tube?
No, they're the same tubes. This is just this is a subset of the data on the next one. This just has a lot more different kinds of functional groups instead of just alkyl groups.
Oh, so you just add more data on your previous figure?
Yes. Yep. Just generalizing, trying to see if we can generalize this trend, because we see really nice trends for all three lines here, but then on this slide we don't. We see kind of okay trends for the alkyl groups for the dipole. The aryls are all over the place, and the other groups don't trend super well. And the red, the functional group charge, also doesn't trend very well, but arguably maybe a little better than the dipole, but still not consistent across all groups. However, the tube charge does seem to yet still be consistent with this previous plot. So you can see this generalizes well to the bottom left figure on this slide. And so possibly the charge on the tube could be much better than the dipole moment as far as a general argument for predicting a redshift. Along each series, or each sub-defect series, so aryls or alkyls or fluorinated alkyls, the dipole does seem to give a pretty good indication in most respects to a prediction of that redshift.
And before
so
you
now
go,
here we can jump.
Braden, so
Sure.
your bottom panel, the green one, this is just the same information as in your top panel, right? You just kind of eliminate,
Yep.
like you change the scale and you show in only green.
Yep.
Means it's only the charge
Exactly.
on a nanotube for all these
Yes.
species which you tried, which means fluorinated
Yes.
alkyls of different lengths, and then for fluorinated alkyls, you also change the number of fluorines in this case. Am I right?
Yes.
Like, because in your previous discussion for the system, you fix number of fluorines. You just changing the length of the chain and consistently changing the number of, with whatever completely fluorinated alkyls of different lengths. And here you really have some hydrogen, some fluorines, right? And you changing the number of fluorines.
Yes, yes, this is a completely different system that we're comparing to. Yep, and on the next slide, I'll be back to my system doing the same analysis.
Okay, so
Yep,
I'm
so the
done
bottom
with
left-
my questions.
Okay, yep. Okay, so for this now, we jump to my system. So now we're doing the full carbon nanotube with my defects. And so here, on these two panels, I'm showing on the top panel the most redshifted position and the second most redshifted position than on the bottom panel. And all of the data on these panels is only with one functional group and the auxiliary group being a hydrogen. So from here,
But this is now the charge on a eliminated, like on your model, or it's a charge coming from the entire system?
the entire system, this is the full this is the full 10-5 carbon nanotube with my defects.
Okay.
And your calculated redshift.
Yep, and more importantly, now since this is my system, we can't use his experimental data, so now we're using our calculated redshift here, and we can clearly see that the trends are not quite as reliable as they were shown to be previously using the calculated charge and the experimental redshift. In either of these plots, the dipole is kind of all over the place. The defect charge is not very consistent across all groups, and the tube charge is also not very consistent across all groups. So this raises a question: how well are we doing with this TDDFT on this level of accuracy? And
I
so
have
here,
a question to probably Brandon. So the previous data, like if you go back to the previous slide. So this data, as I understand correctly, this data come from Brandon. Do they?
These come from
you.
No, the experimental redshifts are from Yulong.
Well, I understand. Experimental redshifts from experiments.
sorry.
But can you make the same figure, but instead of using experimental shift, show your shift between calculated E11 versus calculated E11, calculated E11 versus calculated E11 star? To be consistent.
Yes, I have done that. I've done that with 6.5 before, because I've previously done this, and I see the similar things to what Braden sees. When you use experimental data, the calculated result, the result actually has a good trend if you look at the carbon nanotube carbon. But if you look at, and just general trends with the charge on the functionalized carbon. But as soon as you substitute in your E11 or your redshift as calculated, those trends become much more muddy. I guess they go away to the point where you'll see
the trends don't really go away, because you also have, especially for the second, go to the next slide. And if you look on the O minus, right, your green is kind of straight line, so you can say they follow pretty nice trend.
Yeah, the general trends stay, especially if you limit it to a specific type of functional group. But the the trends within are looking at all of the data, including different types of functional groups, then are not nearly as they're not as consistent. We have trends where if we look at the experimental data versus our calculated charges, every point is in line.
But
Or not
in
not on a line,
experiment, in experiment, this data which you use, they already averaged over ensemble.
Yes.
This is not data for a single, precisely single sample, single nanotube,
Of course.
right? They made many calculations, I mean many measurements, and then kind of average over a range of peaks, right, and take it as ensemble average, which of course
Well, they're in
means,
solution phase.
yes, which means again that you kind of average these values, these shifts, right, rather than taking it specifically at specific geometry. While your TD-DFT calculations, it's really for this specific geometry. You're not having
Yes.
kind of this smooth. And if you try slightly different geometries, let's say you do the room temperature kind of optimization, not optimization, just run dynamics at room temperature, and then take many snapshots, recalculate TD-DFT, average, you probably will see much smoother shape in this case.
Okay.
Do you see my point? So it's not that
Yeah,
something
we've never
wrong.
done that.
Well, I don't say you need to do it. I'm just saying it's clear why you have much more, how to say, much more deviated kind of trends overall from your calculation data, because here you really kind of have like there might be just your geometry. Who knows whether it's really exactly the right geometry, right? So you might be locked, trapped in a local minimum or something like this. So while in experiment, they also might have some special structures, but they already averaged this results over ensemble. So they kind of have a statistically weighted results for those tubes, which kind of gives you the majority, gives you the most probable outcomes. In your case, you really might be more, how to say, sensitive to specific configuration of the tube, which results on this stronger deviation for your trends. But overall trends kind of there, if you can call it trends, because I see the straight
Right.
line.
Yeah. Yeah. Right. And I think we're safe because if we do limit it to an individual type of group, then we're still showing this inductive effect and how it changes
Yeah.
the calculated
Like-
redshift even in that case.
Like if you do the same as you were doing in your 2 slides before, where you're showing just alkyls, right?
Right. Mm-hmm.
Like this one. If you do the same thing with your tube, probably you will see more kind of close to that trend as well.
Right. Mm-hmm.
But
Yeah.
this is alkyls. This is again it's not fluorinated. Is it fluorinated alkyls or what kind of alkyls you showing here?
Yeah. On this plot, the main thing that's changing is the distance between the tube and the nearest fluorine. So you're kind of changing. You're removing hydrogens
it's
and
a
putting
fluorine, it's not-
putting fluorines on there. Yeah.
So you change the number of fluorines in alkyl groups, and number and their position, just number of the fluorines, or you also put them kind of close to the defect, far apart, far away from the defect.
Yeah,
What do
I
you-
guess the fluorines are starting on the outside, far away from the interface, and you're adding fluorines toward the interface.
So you increase the
So you
number of
mod-
fluorines and also moving them closer and closer to the defect site. I mean, to the attachment to the tube. Okay.
Yes. Okay, yeah, so this plot, okay, so on the previous slide I'm showing all three series, but then on this plot we zoom in, and like you said, we can still see that linear trend, but it, like we discussed, is some deviance there. So now we can look at those same two things with one group in a hydrogen or one group in itself, and we can plot the dipole versus the tube charge to see if we see anything there, because we saw trends with the tube charge, so we were initially looking at the dipole, so we can see how well those two things correlate, which is really important for this. And we don't really see any trends between these two variables. So that
Oh,
leads us
and-
to believe that the
And Braden, I'm confused because
Yep.
I think you said like in your, again, go back in your previous slide,
this one.
this one. Yeah. You said that this is a charge of the entire optimized system when you have nanotube, 10.5 nanotube with whatever functional group you attach there, right?
Well, not the total charge, just the charge attributed to the carbon
I understand, yes.
on the tube. Okay, yeah, yep.
So which means you really have this new, like, but you still have this new groups, Cn, F2, n plus 1, which means you vary the number of fluorines on a alkyl group. The length of the
See,
group is not changed, but you change the number of fluorines, right?
No, this
So
is
you-
all my data.
I understand.
This is
So you really have, like, you didn't have this data before, that's why I'm asking. So you really put this fixed carbon-6 alkyl group and change number of fluorines, re-optimize it and calculate, kind of have, I don't know whether you were able to get TDDFT calculations, but you really having this charge for the entire system at the ground state.
no, this is my original system. I haven't added any new systems since
But
for a
your
while. This
original
is my system with only.
Your original systems were not changing number of fluorines. You were changing the number of carbons and fluorines simultaneously.
Yeah, I think there's a typo on this slide. The 6 under the C's should be N.
Okay.
So it's either fully fluorinated or fully not fluorinated. We're changing
I
the
see.
length.
Okay.
Yep. Same as the data shown earlier. Yep. And here, the same data. Again, the 6 should be an N. Sorry, but we see we don't see good correlation between the dipole and the tube charge. So this raises the question: how good is the dipole in general to predict these redshifted species? And that's the main points of this project. So some conclusions from that are we have the functionalization orientation, which allows redshifting from anywhere from 20 to 400 millielectron volts, and then further tunability comes from the group modification, which can add 5 to 100 millielectron volts on top of that. So the dipole. We've noticed that the dipole can be used to compare redshifting in a series of species. So if you're comparing alkyls to alkyls or aryls to aryls, you can trust the dipole relatively well. But when comparing to experimental E11 star shifts, we see that the computed dipoles and charges for the defect, there's not really a general trend across all species. But when we compare the tube charge, we do see a nice trend, a linear trend with that charge, which is something that has kind of been previously shown with the inductive parameter by Yu-Hong's group as well. So the dipole alone is not that reliable in general, and one needs to compare all the inductive effects and the resonance formations to be able to predict these redshifting amplitudes for a wide variety of species. And then acknowledgements, of course. And that's it. Any questions?
What is the reason to separate your data? Looks like you were showing your data for the last slide with data, I mean, not acknowledgements, of course.
This one?
Not conclusions, data. The figures.
Oh.
Well, maybe you're not showing it, maybe it's in your old version. Looks like I have a figure where it says full model R1 over R1 and then PF2 over F.
Is it this one? Hit this one.
So you have a one figure with your 10.5 where you take in the charge versus the shift and dipole versus the shift. For the case when you have different groups and hydrogen, and you already said that you don't see really the same trend as it was noticed in 6.5 tube with comparison
Inside
to
before
experimental one.
conclusions.
Yeah, this one.
Yes.
And in the version which you sent in the email, you also have similar figure before the conclusions, which has both groups identical.
Oh, yeah, I think I hid that slide. I just didn't show it.
But my question, why not to add the same data on one, like why you separate this data into two different plots? Why not just to add the information on the same groups versus information on the one group and hydrogen? Because your dipoles and your charges probably slightly different when you have two groups rather than one group.
Yeah, so, I mean, the main reason I separated them was for that reason. The charges, they might be different, yeah. But the auxiliary group being a hydrogen, I said earlier, produces always the least redshifted splitting. And so putting them all in the same plot would be kind of a mess, and it is kind of a mess.
But you're showing the most redshifted species anyway, right?
Yeah, but all of the, yeah, I mean, I could put them on one plot, but the trends were more easily seen here.
You're saying that if you put them on one plot, then your E1, like the range, X range, will be just extended for much higher energy, because they provide larger difference in energy. Oh, I see. So you go up to 0.32 in one case, and you go in here by 0.23 in the other case. So you have about 0.1 electron volts longer axis if you add the other data. Okay. But you have some overlapping.
Yeah, we do.
Okay.
Any other questions?
I have one. Back on your absorption spectra, you're comparing, what is it? The, like 6 chains of carbon versus 1 chain of carbon. Is there a reason that you're using different lengths of chains in these comparisons, or? Is that like
so this one, right?
Yeah, like why is it C6F13 and CH3?
So the 2C6F13 is part of the alkyl family, and it happens to be the most redshifted species. And the 2CH3 is one of the least redshifted species. So we were comparing and contrasting opposites here.
Oh, okay. So you were just trying to make it as wide of a redshift as possible, basically.
Yep.
Or as wide of a discrepancy,
Yep.
I guess. Okay.
Yep.
Can you explain, like, if you go to the next with the absorption spectra, like where you comparing this figure with fluorines, with where you have just two fluorines attached, or fluorines and hydrogen attached, right? So it looks like you have much more significant difference, because if you, according to your previous results, right, the case when you have a single fluorinated, the longest fluorinated alkyl, like C6F13, and hydrogen, it's pretty much behaves in the same way as 2CH3. Am I right?
Yes.
So that's why I would say, like, if we look, like, we can think about this two fluorinated alkyls versus one fluorinated alkyls. One fluorinated alkyls will be very similar to this red curve. But the difference between black and red is much less comparing to the fluorines, two fluorines versus fluorine and hydrogen. So can you explain?
It's true, yeah.
Can you explain why this effect is more strongly seen in case of fluorines?
Well, purely the fluorine attachment with the auxiliary grouping hydrogen is roughly equal to the 2CH3 on the left figure. So the red lines on both figures are almost overlapping. But the two fluorinated attachments produces a more redshifted. So you can see that in the P+ position on the bottom right. You can see that it's almost 1.1 for that transition energy, but on the 2C6F13, it's more close to 1.2, and so that kind of is a little misleading too. So the red ones are actually about the same. It's just that the 2F system, being the direct fluorine attachment to the tube, produces more redshift.
Well, then the question is, why is it more redshifted?
Well, there's a greater inductive effect at that interface with a direct fluorine attachment than if you put a carbon in between.
On the other hand, you have probably a much stronger dipole moment for C6F13 rather than for the 2F, right?
That's true, but what we've been seeing is that the dipole moment only works for alkyl groups. So with that carbon there, then that dipole moment is more or less trustable. But then when you flip groups around, like putting a fluorine attachment, then you have to look more specifically into what created the dipole, like the charges, because those give more information to the system, as I think this data is showing.
Well, if I remember correctly, you were showing the, like, of course, it's if you go to the orbitals, which you're showing, you're also showing your orbitals for 2 fluorines and then 1 fluorine and hydrogen, right? Can you see any difference? Well, again, maybe looking on this, it's hard to see any difference between 2F and F over H. But I remember in your previous versions, you have really kind of, how to say, you just you have a snapshot
zoomed
around
in.
the defect, zoomed in the defect. Do you remember, or have you checked? Do you really see some difference in the orbital delocalization in these two cases, 2F versus FH?
And maybe more general, very general. You may have even placed in the introduction. Typically, if one has an intrinsic structure and then a defect, there is a chance for defect states localized on the contributed group. But here, your transition orbitals are very delocalized, just in the vicinity. How would you explain it? Like, what is the mechanism of orbitals being delocalized over carbon nanotube rather than being only on the atoms contributed by this functional groups?
By the doping.
Yep.
Yeah. So what I've seen for this tube with these defects is that the ground state structure, I don't see really any charge density on the defects themselves at the frontier orbital level. So the HOMO and LUMO I've looked at. But
Why?
the NT, because the defect doesn't add states to that region, it just changes the symmetry and pushes the band gap closed more so.
Okay.
So that's why, again, the naming doping is probably not really a right way to use it. Like, it's not in the same way as we use doping for the semiconductors, right? Because doping means you really introduce the state, which is mainly maybe slightly delocalized, but it's really introduced by this atom, by your doping, by the atom or group which you add. And here, it's really not really the group. Except fluorines, the other ones not really sitting on these molecules. So it just change of the host orbital rather than coming due to this rather than being localized on the defect, not defect, on the group, on the doping.
Yeah. Yeah.
Did we answer your question?
Yes.
But still would be probably maybe kind of you can connect the explanation for this more significant redshift for the fluorines, right? Not only is talking about the change in the charge, where again, we clearly don't see very nice correlation between charge dipoles and the splitting. There is kind of, especially charge and the dipole, probably not really very much correlated in this case. But maybe you can really discuss it in terms of localization, right? And difference in these orbitals between comparing these two fluorinated alkyls versus 2 fluorines, where we clearly see that in 2 fluorines really contribute, while in the alkyls, fluorines do not contribute at all. It's carbon which is attached. It's really contributing.
even on the NTOs for the P plus and the long chain fluorinated group shown in the upper right corner, you can't see it, but there is a lot of density on the adjacent fluorines as well, 2 atoms away from the tube.
Yeah, but on the other hand, we know that FH, you said, behaves pretty much the same as this not fluorinated alkyl, right?
Yep.
So
And
anyway, I
you
just
see charge density on that fluorine, but not the hydrogen.
Okay, I see. And also same for the alkyl groups. You see something on alkyl, but not.
Yep.
Kind of also see something more on alkyl. Okay, but anyway, so this discussion probably can be added for explaining this the most redshift. Like, of course, it's interesting to know why this species is really the most redshifted. And it looks like your 2F is definitely the most redshifted. If you look at the same, especially at the same position, right? So little, like you can talk about more electronegativity, you can talk about charges, dipoles, as you already kind of did, right? And just looking on these orbitals, you probably can get some difference between 2 fluorinated alkyls versus 2 fluorines and versus this hydrogen fluorines and so on.
Yeah.
Because the nature of orbitals definitely is different, and contribution of these groups clearly make a different contribution to these orbitals.
Yes, of course. Yeah.
Any other questions? If not, no? 1, 2, 3.
1, 2, 3. Let's thank Braden once again. And next speaker is invited to the stage.
Is it just me today, or is there someone else?
No, there is a line of people who want to speak after you.
Okay, alright, well, Solana, do you think I should just do the second half then, or what do you think I should do?
Are you ready? No. But you said Friday, no? Today is Friday.
Who else is supposed to join today?
Isn't Tuesday?
Oh, okay. No, when I asked you this Friday, then I thought it was Friday. Today Friday.
Мне еще ко мне прислали список, там в июле, я просто зашли, потом одно нашли сразу пейпер. Да я просто по отдельности посылаешь. Подожди, ты Дэйна ничего не заметил?
We submitted to GPC short.
Ты мне одну послал в июле. Ты мне одну статью послал еще в июле. Это вот, который GPC. Ты еще Дэйна обещал свою собственную. Я приходила и обещал.
Feel free to keep.
Ты что, ничего не писал?
Wait, so who else is supposed to be going today?
You're
You're going today?
Yes, I'm fighting.
Okay. Alright, well then I'm gonna try and keep this short, because this is just... Really? Okay. Alright. Okay, so a lot of you guys have seen my research before, so I'm just gonna briefly go over it. I worked on cadmium sulfide quantum dots, and most of you guys already know this. It's really annoying to have that not be that. Okay, sorry. So quantum dots have tunable photoluminescent properties, and so we're looking at cadmium sulfide quantum dots because they're generally used in a core shell structure, just because of the cadmium sulfide's band gap. It's just a good way to use like the core shell structure. Sorry, that didn't really make any sense. Okay, I'm gonna keep going. So I know, I apologize.
This is really funny. You given a talk and you say, "Oh, what I'm told to you probably doesn't make any sense."
Yeah, yeah. I realized that
doesn't matter whether it makes sense or not. Just don't tell people that what you're saying doesn't make any sense.
I know. I'm sorry. I just gave another presentation before, and it was on other things, and now my brain is all scattered. So I apologize. But anyways, moving on.
Just focus.
Okay, so the two solvents I used are acetonitrile and propylamine. Acetonitrile is very polar and propylamine is non-polar. And then I used 3 different passivating ligands, thiol, amine, and acetic acid or acetate. and the size of my quantum dot is 1.5 nanometers, which you'll see on the next slide. So the reason I use these three ligands is because thiol, this is the one that my previous research was focusing the most on, was shown to bind very strongly to the quantum dots, so it would be hard to replace with other sort of ligands, which means that it would most likely, whatever properties it showed, would be stable over a long period of time. And then they produce a bright quantum dot and are sensitive to pH, which all of that information, it was shown in the top paper right there, so if you're interested in it, you can go take a look at that. But we're basically just trying to figure out whether or not thiol or thiolate, which is the deprotonated form of thiol, is beneficial to the quantum dot. And then acetic acid is used as a common solvent used in the synthesis of creating a quantum dot. So we were, the second half of my research is looking at like how that would affect the quantum dot if it was postulated by it. And it is also stable in polar and nonpolar solvents, which is really awesome if we're using it for any sort of life applications. And then amine is just a very stable ligand, and has been shown to increase emission in certain cases. So these were for various types of quantum dots, like zinc sulfur quantum dots, and for cadmium sulfur quantum dots, and so and like cadmium selenide quantum dots. So we're just kind of trying to overall round out our knowledge on specifically cadmium sulfur quantum dots. And so I'm not going to get so yeah, these are most of, oh my gosh, this is so annoying. These are what our goals were for the overall research that I did for the past year and for the summer. So we were trying to figure out what the effect of the solvent was specifically on the structure and the lower optical transitions, whether or not thiol or thiolate had positive or negative effects on the quantum dot, and then trying to decipher which ligands were the most comfortable on the quantum dot, and how they interact with each other, whether or not that's through the proton, or whether or not they form a structure themselves or complex themselves. And then my new research is focusing on how the stoichiometry of the quantum dot affects the photoluminescent properties of the quantum dot. So we'll get into that a little bit more later. And that also goes hand in hand with the ionic versus neutral, so the charge of the system. And then the questions that have been addressed are, specifically I figured out whether or not including sulfur we'll go over that later, whether or not the basis set affects a more intense basis set affects the computational outcome of the quantum dot, the effect of the thiol and thiolate ratio on the photoluminescent properties, and then some of the effects, this is a very broad statement and a little bold, but some of the effects of acetate and acetic acid on the quantum dot itself.
But again, you return back. My understanding, you're not just looking on the acetate by itself. You see the effect of acetate with a silyl,
yes,
right? So
yes.
kind of effect of acetate-silyl interaction.
Yeah, I should have.
So it's not just isolated
yes.
acetate ligands. You have now two different types of ligands, acetate and silyl, or sialate and acetic or whatever, right?
Yeah.
It's kind of combination of these two, and see how this affects the properties of quantum.
Yeah, absolutely. It's not just the acetate, but the overall system plus acetate and plus extra cadmium. And then methodology, since other people want to go today, you can ask me about it if you want, but the general functional group that I use is the PBE1 PBE, and then I use the 631G star for the smaller basis set, for the smaller atoms, I'm sorry, and then Lano2DZ for the cadmium and the sulfur, and then I calculated and then CPCM for the solvents. And then I calculated the binary energy and looked at the projected density of states. And then this is the Gaussian distribution function specifically for the projected density of states. And then the same thing is like the same basis set, same functional, same everything is used for TDGFT, and then a slightly varied, well, same equation but used for slightly different things is calculated used for the absorption spectra.
Is Levi around or not? Guys, can you
Yeah.
hear?
Yeah, sorry. Someone came to talk to me right as I was leaving.
But before they can
What's the
hear us.
question?
They might be able to hear
Hello?
us.
No, we
might
can-
not be able to
Might
hear
hear
them
them.
since they're not on their.
Can you hear us?
Hello? No, they don't have us on the screen.
No, they do.
No, they don't.
Because I had a question to
They
Levi
can't
for
hear
the
us.
previous slide. We had the formula which you...
Wait, hold on.
Oh yeah, the
With
way
the
that
I, and I
No,
wanted to
it's
ask you,
unmuted.
Yeah.
Can you return back?
Yeah, it's not gonna be on there because
They-
So we have the
We've
syntax I.
been still all the time.
Levi is here, so then can he explain somehow, maybe later
Do
on?
you know how to switch thumb to the board? Because I don't know how to do that.
Can you hear us?
Why he needs the second index here? What's the second index stays
We
for?
need to be on the main screen in order for that audio to get through.
Yeah.
We can hear you now.
Oh, there.
You
Okay,
hear
what's
us?
the question?
There's on the Gaussian distribution function, there's an n and an I. What is the I used for? Can you look at my power? Does it say?
Did you upload it to the Gmail thing?
No, I did not. Here, why don't we flip
Can
back?
you
They
can
cannot
you
see the
focus
slides?
on the TV instead of the screen?
If I can find the remote. There it is.
This?
The N and the I.
The
I
TV
don't know
doesn't.
very clearly.
Oh, this
I
one.
need
This
the
one?
density eyes.
You're gonna have to guide me.
Yeah.
One is the state, one's the energy, right?
Okay, no, that way more, and then that,
Oh,
and then N. Be good.
Can you increase? Can you zoom in?
I don't know how to zoom this
Maybe
one
it's-
actually.
There
Oh,
is
here
a
we go.
zoom.
Ah,
Good job.
Perfect. So this part right here, and here.
Oh, so that is for the projected density of state. The N is for the electronic state, and the I is for the fragment that you're looking at. So the A.
But then,
Uh,
Levi, we do not sum over fragments. We actually make, for each fragment you have special doors. That's
Yeah,
why
so I guess-
you should not really sum over the fragments. You actually
Yeah,
separate
so-
the fragments. So your I
That's-
should be taken out from a sum. Do you agree?
Yes, and then it should be like A subscript I or
You
superscript
can use
I.
subscribe, but you should get the subscribe I from the sum because right now
It means on the left hand side. A sub I.
Yes.
omega.
So A of omega, it
A
could
sub
be
I
A sub I of omega is equal to all of it, and then remove the summation over I.
yes, this is yeah, I agree, right? But
Yes.
in this form, it looks like you sum over all fragments, which means you return back just to the regular doors, not projected.
Yes.
Okay.
Omega should be new, right?
Yes.
Yeah, so
Omega
it should
is
also be
subscribe
new.
L.
Because it's omega on the left side hand side, but it's new on the right.
Oh,
hand.
yeah. Well, yeah. But this is
Also,
probably a
notice-
typo.
A stands for density of states. S stands
No, so A is the percentage of each fragment to the total density.
No, and
So
on
it
the left
de-
hand, but on the left hand side you also have A.
Yeah, I guess
Two capital
the
A's.
A
Yeah.
on,
It's different.
The
Probably
A
it's not a
on
good
the-
idea.
yeah.
Probably you should
Yeah.
get B instead of A.
Yeah, okay.
It should be different letter here. Otherwise, it's confusing. Yes. Okay, so be careful. But this equation was again. I was asking Alisa. She said, "Oh, I just took it from Levi, so all questions to him."
I can't. I can't answer that. So, but for my paper, that equation is on there. So
Then it has to be
We'll
changed.
have to take a look at it. Yeah. I
We need to
can't. I
return
don't
back
know how
to
to.
the-
So we don't need to hear to them
No,
Yeah.
anymore.
We have to skip to the mode
I
where.
mean,
But
I can just present on this. That's fine too. It's
they
fine.
can communicate with Jebet and tell if we need to
switch the mode.
switch the mode.
Yeah, that works.
Somebody has to move us back.
Okay, so
And then,
this should be basic stuff for you. I've seen this before. This is my structure. This is 0.5 nanometers. And then A and C are 2 coordinated, so the most reactive layers. And then B and D are 3 coordinated and less reactive. So that'll come into play later. But
why D is less reactive? Isn't it supposed to be more reactive because it's surface layer?
But it has 3 surrounding. It has 3 bonds, so it only has 1 unsaturated bond. So it's less reactive.
So you have cadmium 3 coordinated cadmium versus 2 coordinated. And guess which one is more reactive? Of course.
What about the
coordinated
H
is
cadmium? There are cadmium
So
on the H.
this, you can't see it very well, but sulfur's on the outside of the bottom, and this is on the inside.
Oh.
And on the top, it's all cadmium on the outside.
Oh, okay.
So like it is still surface, but it has 3 bonds. So there's only 1 free bond to interact with. So.
And of course, these 2 bonds completely change when you optimize the structure, right?
Yeah.
So then those which were 2 coordinated, they kind of get into the position having 3 neighbors. So they kind of self-heal themselves.
Yeah, but for the purpose of like adding specific layers of atoms, not atoms of like molecules, we put them on layer C if you're interested in how they reacted to a more reactive surface. So yeah, and then we have thiol and thiolate, which that tends to do coordinated thiolate. So I'm gonna. This is just kind of a. I had a lot of questions about this before when I presented, which is this is the binding energy, and a lot of people ask me about how is it possible to have a positive binding energy for this system, so I thought that maybe it was a mistake on my part, so I took this C layer here because acetonitrile is the only solvent to have, well I only did 2 solvents, but acetonitrile has the positive binding energies, and then I took the C layer, which is the most reactive, and it kind of has a dip in the binding energy, so it's more it's a stronger bond. So I decided that I wanted to try it with different basis sets just to see if the basis sets had anything to do with the value that I was receiving from this point, from this calculations. And so here are the different basis sets. This first point here is using Lano2DZ, which I don't know why I didn't write it bigger, but that's what L stands for, is Lano2DZ. So this, it has the cadmium and sulfur, all cadmium and sulfur, including the sulfur from the thiol ligand, incorporated in the Lano2DZ, where the rest of the smaller atoms have 631G star, and then it progressively gets more complicated.
So what is the difference between first and second?
So this one has all sulfur, so including the one from the thiol, and then this one does not have the one, so the ligand is all.
So you treat your sulfur from thiol differently comparing to sulfur from the quantum dot.
Exactly. And you can see that it slightly increases the strength of the bond towards the end with the more complicated basis set, but it took me like 3 weeks or not 3 weeks, but like a solid 2 weeks to run it, and it didn't significantly decrease.
So what you're trying to say,
energy.
When you go into increased basis set, you see the significantly increased computational time.
Yes,
comparing to your very first or second case.
Yeah, this would take, for the system that I was using, which is thiolate with a proton on it, and thiol and thiolate with no amine, by the way, so like it's a very simple system. This only took probably 10 hours, and that was going on weeks. So
the last one.
Yes.
But what about if you're just increasing your basis set for the ligands? Did you also notice that it's significantly increasing the time of calculations, or not really?
I know I couldn't tell you for these two. Well, I know that this one took longer, but this one was roughly the same
well,
as that
because
one.
it's only one sulfur different.
Yeah, exactly. I don't know for the middle one though. I didn't look at it. But especially for the end one, it was just a substantial increase, and it didn't necessarily affect the binding energy enough for me to think it was worth the computational cost to go back and redo all of my research. So, anyways, that was the explanation that I came to for that. And then I also had another question about whether or not the thiolate H here was, well, this was a trend on each layer of the quantum dot, or if this was a anomaly and just happened to have one bright, like that specific layer had one bright transition, and these are all on layer A. And so this is the.
But can you again just remind what exactly is the trends you're talking about, and then you can discuss specific of this specific the brightest or whatever.
Also, I just noticed a typo. I don't know if this does do this. I changed this before and it must not have stayed. But this is amine and that's noamine instead of propylamine. Just clarifying that. So what we can see.
Okay, again, if you go with columns, the first column is covered with amines and only one sialosialate. The second one, bare dot, with one sialosialate.
Yes, exactly. And then top is propylamine, and this is acetonitrile. So here we can see that there's no completely dark transitions, but none of them are extremely bright. But you can see a sharp increase. I only included the first 2 or 3 transitions because it was just kind of overwhelming to include more. So these are for the first roughly 3 or 4 transitions, and they're not dull, but they're not bright. But you can see in propylamine, in propylamine with noamine, you can see this substantial redshift in the thiolate without a proton, and then both thiolate with a proton and thiol with a proton have very bright first transitions. So I was curious to see whether or not thiolate continued to have bright transitions on multiple layers rather than just layer A. And so on my next slide, I went into it a little bit more. So this is calculated for thiolate H in propylamine with noamine for all layers. So depending on the colors, is the layer. So what I was curious was whether or not a network had anything to do with the oscillator strength. So what I mean by a network is, you can see here, this is a depiction of thiolate, and this is a depiction of thiol. So if there's some sort of, if this bond shortens and this bond shortens, or like rotates, so that they're it's in between thiol and thiolate with a proton on the surface, whether or not that has anything to do with the oscillator strength or where it is on the energy, as far as where the first transition is. And you can see here, layer C and D are the 2 shorter ones because it has 2.47 and 4.1, which is roughly, that means that they're very close together. It's extremely redshifted, and the first transitions are fairly bright. And then at 4.7, it's more.
But again, for you, am I right? Is that for your C layer, you start with thiolate H, right?
Yes, always.
Initially.
On all of these, yeah.
But it looks like, because I remember your previous presentation, it looks like in the A, B, and D, if you start with thiolate H, it leaves as thiolate H. But if you start with thiol, with thiol H, and this, it starts as thiol. But on a C layer, right, it's you start with thiol, it returns to thiolate.
Yes.
And if you start with thiolate, it has, not like this network, have this tendency to return back to the thiol rather than being a thiolate.
I would say it's a solid in-between state.
Okay, yes. So that's why probably you have such a very big difference with your C, because it's really not anymore thiolate, it's this network position, right?
Yeah, and then you can see as the network decreases, it gets more and more blue shifted, to the point where like one thiolate on the surface.
So you have completely 100% thiolate on A and B, right?
Yes,
For sure.
yes. This one is like slightly interacting, but I just think like layer A, but I think that's just a like circumstance of where the proton was in relation to where the thiolate was. I don't think that has anything really to do with like the reactivity of layer A. So I think layer C is the one that really creates the network every time. Anyways, I thought that was pretty interesting, just so that you could see that clearly the network had something to do with the the gap in the absorption. So yeah, that's kind of the.
But again, return back. So first of all, it looks like you have this. If I'm comparing black, red, and gray, which is right now hard to distinguish from the black, but we can imagine. So except your black color, your first state in red and gray is optically inactive.
Yes.
Or very much weaker, right? And then it follows with a bright one.
Yeah.
While for the black one, for the A case, it's kind of swap. Your first is optically active, the next one very close in energy is kind of going down.
Yeah.
But for the blue, you have, it's much more redshifted, like you have additional peak appearing. But this peak, in all the low states in this peak are maybe not very bright, but they're kind of optically active.
Slightly.
Which again, if we're thinking about emission, which happens from the low state, you expect that in a case when you really have this network, kind of in between, not silate exactly, you have redshift for the emission comparing to the pure silate case, right?
Yeah.
On one hand. On the other hand, you probably expect that your emission probably would be higher.
Yeah.
Especially if you compare with the case B, the red one, and the case D, the gray one, right?
Yeah. Yeah.
With only exception would be your black one, A, where you
It's
really
way
have
up.
the very low state is very bright. Then maybe this case it also would be emitting.
Yeah, that's
with a
the-
blue shifted emission. Right?
That's the downside to A and B is that they do have those. Well, A, B, and D is that they do have those really dark states. But
Okay.
yeah. So.
But overall, we again maybe not 100% evidenced, but looks like that if you have really this in between this network position, so the emission will be not probably quenched.
I don't think so.
It will be redshifted, but not really quenched.
Yeah. Which is, I think, an interesting thing to like look into further. But that's what I have for right now. So. And then that's kind of it for the. That was just the questions that I went back and answered for my. Oh my goodness. For the one thiol, but now I'm kind of moving on to the full passivated. So there's I don't think I mentioned this earlier, but there's 21 cadmium binding sites on this particular quantum dot. So then there would be passivated by 21 thiols or thiolates with the proton. Obviously, I can't just have thiolate without the proton because that would be an insane charge and just not realistic. So I started with thiol in these two here and thiolate with these two. And something that's really interesting to note is in propylamine, you can see some extreme deprotonation of thiol to thiolate. And that moves like over, I thought I put that one here. Sorry, give me a second.
You have 9 deprotonated.
Yeah, I put it on the wrong side. But yeah, so this one moves like roughly 1 angstrom, which is a significant distance for that proton to travel. Whereas this one starts with thiolate H and is like turning into protonated thiol, and that barely moves. It moves like roughly like 0.1 angstrom. So it is moving, and it is like looking isn't the right word, but directioned towards the thiolate. So you can see that it's clearly a network, and that if like any sort of perturbation were to happen to the quantum dot, that it would be possible for that proton to return to the thiol, return to the thiolate and create thiol. But in acetonitrile,
so overall, again, we can kind of conclude that either you start with a full passivated thiols, you will end up with, I don't know what, did you figure out the percentage?
Yeah, I have it. It's all of it's on the next slide, so I don't know why.
But you have 21, right?
Yes.
And 9 of them are deprotonated, so it's kind of not exactly 50, but
it's
4 to
3
ratio.
Yeah.
And return back again.
I know. I don't know what I was doing.
Here, if
but
you
I
start
messed
with
up.
thiolate, you also have in kind of a little bit, majority of them stays as thiolate, but I would say close to 50-50%, like almost equal distribution with a little bit preferential kind of
thiolate.
Going either to thiol or to thiolate, depends which of them initially you started from, right? While in acetonitrile, you clearly see a significant difference between between this new species, new network species. Right?
Yeah, so these ones, so this one, you can see that thiol moved over an angstrom, and then here, this, it is moving from the thiolate to the surface, no, from the thiol to the surface, but it's 0.1 angstrom just like that one is over there. So the network is there, but it's just not as expansive as it is in this case up here. So I would definitely say in propylamine, it would tend to be thiolate with a proton on the surface rather than thiol, but in this case it doesn't really seem as though it significantly matters, but it is clear that this could change into thiolate from thiol. But something that I found was extremely interesting is that when you start with thiolate, there is no tendency to turn back into thiol.
Which again tells you that as soon as you have a deprotonation in the highly polar solvent, you probably don't have this dynamic equilibrium going back and forth. It stays in its deprotonated form rather than returns back.
Exactly. And it's not even, none of them are even oriented towards thiol, well, the thiolate, so it has no want to go back into that direction. So anyways, that was something that I found interesting about that, and then I don't know why I put it on the next slide, but I did. And so that was the information before that I talked about. And here are the ratios again. The green is always the thiolate network. It corresponds to the key, so if you're confused, just look at the key. But something that's very interesting is the band gap here is this band gap is like roughly equivalent to that band gap, but you can see very clearly that there's a trap state created. This is set up exactly like the other side. I didn't mention that. Where this is propylamine and then amine and no amine. But you can see very clearly that there is a trap state. However, the band gap is larger. So it's very obvious that the thiolate does increase the size of the band gap, but will create a trap state. And then the trap states are created here as well. So overall, acetonitrile has a tendency to create trap states. And then here, there is no trap state present. And then here as well, I don't believe that there is, even though the green is overlapping with the blue. I think the blue still is bringing it out.
So when your portion of thiolate versus thiols is kind of almost 50 to 50 or close to it, right? So then you really don't see this effect of...
No, not really. But as soon as you start seeing more of one or the other, then this becomes very prevalent that there are trap states. Is there any questions about this? Good? Yeah? Okay. And then this is just kind of summing up what that full thiolate passivation was about. This is the absorption spectra for the full thiol. So thiol is in black and thiolate is in red. And here in the nonpolar solvent, which I didn't label, but this is propylamine and that's acetonitrile. They're roughly the same, like this is slightly red shifted, but they're not terribly far apart. You can see the drastic difference in thiol and thiolate, which I believe is completely due to...
So again, for your... can you return back to your... so the black on the right in acetonitrile, it still would be... majority will be thiols.
Yes, majority thiols.
But you have a little bit of thiolate present.
Yeah.
And for the red, for the acetonitrile, you have completely 100% of thiols. Thiolates.
Thiolates, yes.
Wait. Left and right, what is the difference?
This is propylamine and that's acetonitrile.
And it is not...
You return back to the...
It is not labeled.
It is not labeled.
No, I know,
but
I
it's
forgot
kind of
that.
follows the same idea of this...
This is actually
density of states.
flipped upside, but like, yeah. So I completely I labeled it and I sent you the wrong one, but it's okay. Yeah. So this is propylamine and that's acetonitrile. So this is has to do with this is full thiolate and this is like mostly thiol, which is I think why that there's such a large difference between the two absorption spectras. So, yeah.
But also, again, not a big difference, but if you look on the black with your A case, right, you have these two states which are kind of optically active,
Yeah.
and that's the lowest one, while in in a red case where you have more silate, a little bit more silate, the low state's really dark. Right?
Yeah, completely dark.
And if you go back to your acetonitrile, then in both cases you have low states being significantly.
Yeah, that's kind of what I concluded is
depressed.
acetonitrile is just not fantastic for the optical properties of this specific one.
But you again looks like if you have majority of sials, well, it's a kind of equilibrium concentration, but with a little bit preferential kind of equilibrium towards sial, you probably expect that your low state would be bright if it's not a very polar solvent, right?
Yes,
and
absolutely.
you expect that your emission will be improved.
Yeah. So in nonpolar, thiol is the more optically active, and then in polar, it doesn't matter. They're both. I mean, you can see the increase, the sharp increase in thiol, which is like, is good, but still the first transition is dark, so it's not completely amazing. And then here's the overall absorption spectra, and this is kind of sitting like in a different form of what we said before. We were just trying to see how bright the quantum dot could be eventually, and so
This is not bright. It's absorption spectra. How much it absorbs? Where does it absorb like?
yes,
Because it's not emission spectra, it's absorption
That's-
spectra.
I must have said the wrong thing. I don't know.
You said like how bright the quantum dot is. Bright means if it's emit light.
Yeah.
But here you're looking on how, like, what exactly is their energy range where it the most absorbs.
Yes, I knew that. I just said it. I said it wrong. But with my conclusion for this entire graph here is that with anything over 60% thiolate, which it could be lower, but I don't have any. I don't have calculations on that. It creates this little hump here, where it's not absorbing at a larger rate like thiol is, and that same trend is seen over there. So the greater percentage of thiol, the more intense these peaks are towards the redshifted area of the spectrum.
Like again, in both cases, in both solvents, you have the kind of active peak, the most active peak in a case of you have silate enriched system, right, at around 3.5 electron volts. And then you have a little bit bump with redshifted, and and pretty much the same for sials, right? So this 3.5 peak is also present when you have sials as well, right? But with sials, your low energy peak is much more pronounced, right?
Yes.
Again, either in acetonitrite and propylamines, and in propylamines, this low energy peak is also having kind of high intensity comparing to the acetonitriles.
Yeah, and then
So which again looks like overall the effect of solvent is probably more pronounced for the sial case when you have more sials rather than when you have more sialates.
Yes.
Yeah, because the spectrum of sialate in both acetonitrite and propylamines looks much more, similar rather than blood curves in these two pictures.
Yeah.
Lisa, Levi wanted to know the relative intensity of the first transition in the 4 cases, I guess.
4 cases?
I guess he meant. He said 4 cases. I guess there are absorption spectra of the 4 different cases.
These are 4. Is this what he's talking about?
There are 4 lines.
There's 4 here. Is this what he's talking about?
Oh, maybe he's asking. Well, technically, what you can do,
Can we just put him on the screen? I don't know what he's
Yeah,
talking
maybe.
about.
Yeah, let's make him.
We can.
But I can guess. Maybe he's thinking about that. You have on left and right panels. You have different geometries, right?
Well,
your geometry is different for these 2 cases. So technically, you can take the geometry which we obtained from optimizing acetonitride, 100% and whatever more dominated sials, and recalculate DDFT in a
No, they can't, Levi.
propylamine and see how this different concentration of sialate, right,
It doesn't matter.
will be
They could always.
affecting the
I see what you mean.
So
Yeah.
maybe I'm not sure 100%
You
what
don't want
exactly his
space.
question is, but maybe he's asking like, what if you take all 4 geometries and calculate in the same solvent?
Yeah. I understand.
Because right now you're looking on the geometries which you obtained from the optimization, right? And then you calculate the TDDFT from optimized geometries. But we can take the same geometries and recalculate it with either this or
He
that.
wants the relative intensity.
Are you talking about whether or not I multiplied it?
Relative intensities are on this axis.
They are the same. They're multiplied by 100, just like
If
you did
he
over
wants
here.
to come in the screen, I guess he has a more long distance.
Oh Jesus.
It was, this was Levi just asking.
Now everything's gonna break.
So can you hear me?
Yes.
Yeah.
So the reason why I asked the relative strength of the S1s is because talking to the experimentalists here at Lanel, they do not think that if your solvent is amine, so propylamine, they believe that propylamine would take away the proton from the thiol, which means you only put thiolate on the surface.
Well, that's what
But-
I saw.
No. The proton won't go to the surface, or it will go later, but it will initially be a thiolate, which then means that the surface
Levi.
should have. Yes.
Levi, did you remember the email from Sergey Ivanov?
Yes.
So he kind of addressed this issue. So just looking on your pKa, you expect that yes, amine will deprotonate the carboxylic groups with the carboxylic acid, but not really the sialate, the sial.
I feel like this is
I thought.
another time.
Wouldn't it pull
'Cause
it
I can't answer your question.
Carboxylic?
So I guess the main thing is, while we're thinking about this project, it might be a good idea to think about the proton, if the solvent can take away the proton, because if propylamine does from the thiol and it makes thiolate, it might actually be that the acetonitrile is a better solvent because it won't pull off the proton, and if the thiol goes onto the surface, it is, I thought, more probable that it will stay a thiol than convert to a thiolate with the proton on the surface, which
But
then,
then you need
if
to balance the charge. Then you need to balance the charge. Then you're talking about different stoichiometry.
No, the thiol is a thiol, so it's net neutral, and it goes on just like an amine, so you can do a stoichiometric quantum dot.
Wait, okay, you need to start over. What is your question?
So my question was leading to a statement that is, it might be prudent to think about the physical experimental conditions rather than just going with our theory, because
So,
it might
okay,
be
great.
that.
This is what you will do when you return here. You will start with thinking about the experimental conditions and modeling it, okay? But now
Okay, good.
we cannot just guess, right? So this is the data which we have.
But they are the same, like they're multiplied by the same amount. So if you're asking if they're like I have all the information and I can give it to you. So yeah, is that good? Can we talk about it later?
Because if we don't have data which looks like you're asking something which we didn't calculate, then what exactly is the question? We need to calculate it first and then compare. Right now, we don't have any other data than those which are shown on the plot.
And I'm not saying that you need to do more calculations. It's just food for thought.
Okay. Okay.
Keep explaining so that we don't waste time.
I can't.
She can present on the TV and you can.
Okay, so we're gonna move on to the new stuff that I've been doing over the summer, which I only worked on for a couple weeks because I had another job. So,
you can use the big screen now.
So, I'll try and answer the best I can, but it is still fairly new. So, we were trying to figure out whether or not the stoichiometry of the quantum dot affected the brightness of the quantum dot, and something that Solana made known to me was that acetic acid tends to deprotonate into acetate when in presence of the quantum dot. So we were trying to look into whether or not acetate affected the quantum dot, but since acetate has a negative charge, we need an extra cadmium so that we can start balancing charges because we can't have a crazy charge system. So, yep, this is what it looks like before optimization. Well, this part is optimized in a solvent, and then I placed it on there just to save some time computationally. And then that's after optimization. And it looks a little weird because it's not like in the normal layer, but this is exactly where you would expect it to be if it was following this trend. It's not any further away than it should normally be. So that's what that looks like. Okay, top is the direct density states, and bottom is the absorption spectra. So for each system, I included a little picture here so you can understand what I was modeling. Here is a thiol, and here is an acetate. So this overall system has a charge of +1. And so then I just optimized it to try and see. This is after optimization.
Which of them interacting with this extra cadmium? Sialate or sial?
They both are. The extra cadmium is right there.
Huh?
They both are.
They're both to the same cadmium?
Yes. Yes. I have to go back and model it some different ways, but this is how I started out doing it, so this is what I have results on. And if this doesn't prove to be useful in the long run.
In other words, this extra cadmium is shared between sialate and
between thiol
and carboxylate. Okay.
Yeah. Just to see kind of how it interacted and if anything interesting happened. And you can see that the contribution of thiol and acetate is extremely not even close to a trap state. And that's
the gap.
What? Yes.
Not close to the gap.
Not close to the gap. And that is similar for the thiolate and the thiolate with a proton. The one issue I had here was I just not really thinking too much about it, put the proton too far away so it wouldn't interact with the acetate. So I'm like running a calculation right now where the proton is on the surface of layer A instead of on B, just to see if any interaction between acetate and that extra proton could occur. But for right now, that is what I have. But what I thought was really interesting is even with that extra proton on the surface, the thiolate gap, well, the thiolate contribution moved significantly more towards the gap, and that looks roughly like it did with the quantum dot without any acetate on it, which I thought was pretty interesting, just because, like, I don't know why it looks like that. So, yeah, anyways, that's something that is there. With an absorption spectra, they roughly look the same. The neutral systems especially look almost identical, except for the first two transitions are switched a little bit, but they start at roughly the same energy. But they're not terribly different between each of them. And I believe that I didn't include it on here, but they look very similar to just having an acetate on the surface of the
which solvent is there?
This is all in acetonitrile. So I haven't gotten to calculating it in propylene, so it's all in acetonitrile. I definitely should have mentioned it. Okay, any questions about this? No? Okay, did I remove? Okay. So these are the initial structures that I started with, and these are the end structures after optimization. And here I included all of the cadmium bonds, so specifically the extra enriched cadmium to the cadmium of the surface, just because it was a lot easier to understand how far away it was being pushed from the quantum dot based on that particular bond. And here you can see this is the quantum dot here, and it makes its own complete little shell, and the acetate is kind of blocking the extra cadmium and pulling away. And so if it was in a solution, I'm assuming that would precipitate out of the solution. And then this thiol is just kind of kicked off, which I think that's because it was interacting with the extra.
With this complex.
Yeah.
This complex.
Yeah. So I think the next step would be to move this acetate someplace else and put a thiol there instead and see if it continued to make that same jump off. And then here the same type of situation is seen where the thiolate is kind of pushed off the surface, but it is still.
Now your cadmium is kind of stealing by sialate.
Yeah, which is slightly interesting. But you can see how much further away that that cadmium is than over here, and I believe that it has something to do with where I originally placed it, because you can see between each of these gaps is roughly 2 angstroms. Well, yeah, roughly at 2 angstroms. So if I were to do this again, I would make sure that they're all at the same length, and then recalculate it just to see if they all like ended up at this length, or if it was just because I put it further away. And then what I thought was extremely interesting, the most like relevant thing to this, was if you created the same system and put a proton on the surface, even if it was on layer B, so it was fairly far away, the thiolate is pulled from that complex back down towards the quantum dot. And then that little acetate cadmium bubble thing kind of is pulled away from the quantum dot. So that's something that.
And what is your sialate in this case?
The thiolate is right here. It's hard to see.
So it stays on the surface.
Yep, stays on the surface, and it's pulled towards the proton, which is really interesting because this is very clearly it was the same.
Like looks like you have 2 limiting cases, right? One case, or actually 3 limiting cases. One case you really just completely disattach in both sialate and carboxylate groups.
Yeah.
But maybe again it's because your geometry is really very awkward.
Yeah.
The other case, when it looks like your carboxylate stays on the surface, they do interact with the quantum dot surface.
Yeah, they're very close.
But this extra cadmium is kind of taken out, and you create in cadmium sialate something which kind of moves out, right?
Mm-hmm.
And then completely opposite case when you really create in the case of kicking out this cadmium carboxylate complex, but sialate stays. Is it sial or sialate, by the way? Sialate?
That's thiolate, and the proton's on the surface on that end.
So sialate stays on the surface of the quantum dot.
Yeah, specifically due to the fact that the proton is on there.
So at least you were able to see the case when you're really losing the cadmium sialate complex.
Yeah, exactly.
Leaving the sialate on the surface. And completely the opposite behavior. Sialate complex stays, a carboxylate complex stays on the surface, but you're losing.
Yeah.
Oh, it's not really carboxylate complex, it's really carboxylate groups.
Yeah.
And cadmium is kind of probably losing, and you're losing this extra cadmium anyway. Okay.
Which, this is roughly the same as that. Like I started with, it's in the same position as far as on the outside of the quantum dot. So you can tell that the pull towards the quantum dot is very much caused by that proton. Yes. If I were to do this next, I would put the proton on layer A and see if it went the other direction, or even put the proton on the other side of the quantum dot to see if that even kept it there. And yeah, do you have a question? Okay. And then this is the exact same structure, like the same layout as the previous slide, where this is, okay, never mind, sorry, I take that back. This is 2-acetate with no thiol on it, or thiolate, or anything. It's just 2-acetate with the extra cadmium. And so this is what the absorption spectra would look like, and that's what the DOS would look like, the PDOS. And so you can tell that this is at roughly 3.2, and it's a fairly bright transition. Not bright transition, but it's not dark. And then for thiol with 2-acetate, that's supposed to be 2-acetate. This didn't update any of my updates. Anyways, this is almost identical to this absorption spectra that we see there, and as well as with the 2-thiolate and 2-acetic acid. It's very much the same. So the acetic means that the proton is on the acetate rather than on the thiolate. So all these systems are neutral. So, but you can tell that they're very much similar as far as their absorption spectra, and there's not a significant difference between them. And I think that's due to having more acetate. The quantum dot takes on some of the acetate characteristics rather than the thiol or thiolate characteristics. but I definitely need to look into that some more. And then these are some more systems that I've looked at, where this is the extra, right here, is the extra cadmium, and then there's acetic acid with the thiolate. Just trying to see whether or not the proton preferred to be next to the acetate or on the thiolate. You can see here that it prefers definitely to be on the acetate. And then here is the starting system where you start with thiol and then two acetate molecules, and then at the end of it you can, like, this is before and then after you can see that it definitely prefers to be on the acetate molecules rather than on the thiol. So that was something that you could look into in the future as far as if you wanted the thiolate characteristics. This might end up deprotonating thiol into.
But this is optimized or initial stuff?
This is optimized. This is initial, and that's optimized. So those two are the same, except for before and after. If I were to continue doing this, I would separate them further than they are originally, because this is very close. It's not as close as it looks on this particular view, but I would try and put them further away and see if they were to continue to deprotonate like that. And then these are my conclusions. So this is specifically for the first part of my research. The more complex basis set for the sulfur atom didn't really affect anything. Propylamine creates more networks than amine, so if that's what you're, not amine, oh my goodness, than acetylnitrile, so if that's what you're looking for, that's the way that you could do that. And then the network that's created from propylamine, the more redshifted the spectra is. And then for the full thiol, propylamine causes thiol to deprotonate more, which we talked about. And then having more than 60% thiolate reduces the redshifts the spectrum, as well as reduces. Okay, that was not right. I'm gonna move on. I'm gonna come back. Okay, no, I got it. Okay, so it just reduces the oscillator strength of the first few transitions. Compared to, yes, it red shifts and blue shifts, but both of them are decreased. There we go, got it. And then for the thiol and acetate system, with one acetate and one thiol, the effects of the thiol can be felt on the quantum dot, and you can see it. But with two acetates and a thiol, it has mostly acetate characteristics. And then more than one acetate in certain situations, I should have put that in there, causes the extra cadmium to dissociate. And most acetate complexes, I haven't come across one that does, but I'm not going to say all of them, have no dark transitions or trap states. So yeah, that's that. Any questions?
Let's thank first. And then give chance to everyone, or whatever, who wants to ask questions, ask more.
In your first conclusion slide, and go to the conclusion slide. What is the previous one?
Last?
That's the first
Oh,
one.
this is the last one.
Yeah.
Okay, I don't know. What is the meaning of bullet number 2?
This one?
Yeah. 2 acetate has acetate character.
Yeah, so I'm talking about, okay, so here you can see that it's like slightly, it's slightly shifted, and I think that's due to the thiol being present rather than, and then in here it's completely, like, it corresponds almost directly with the acetate. We try again. Okay, so this is with just 2 acetates. So there's
Okay.
no thiol present.
Oh, acetate character means that character.
Yes. So this is what I kind of set as my baseline, as far as this is a completely neutral system, this is what the acetate would give to the quantum dot. And then you can see here it's only slightly, but with one thiol and one acetate, you can see some redshifting just in the absorption spectrum. Not very noticeable, but it's still there. So.
Is it because of only one thiol here?
I think it's because the system's not neutral. But I would have to look into it some more.
It might be charged, it might be. But definitely these transitions, right, not really involve any ligands. It's pure quantum dot to quantum dot transitions, and all the change happens due to the change in the geometry and kind of sharing this distribution of the charge density due to the present ligands, but they're not really sitting on ligands.
Anything else? No.
More questions, 1. More questions, 2. More questions, 3. Let's think. So there are a couple of volunteers who wanted to present.
Couple?
It's
guys. It's already 2 hours past. What do you mean another 2?
It's
presentations.
Let's make
Are you
them
serious?
quick. Let's make them quick.
Well, I see the. Okay, let me just kind of comment on this. Of course, we can put 2 presentations. Everyone keeps silent. Everyone doing their things. The person in front of us is jumping, running, crying. We just don't pay attention. 15 minutes done. 15 minutes done. The question is, do we really need to do it? What exactly is the purpose of such presentations?
We can make.
If no one cares what the other person is presenting.
We can make it free will attendance, and whoever wants to hear can stay. Whoever has other.
Can we just transfer it to a different day? At least one presentation.
I would be fine to move mine to Tuesday. I mean, mine's just like a more updated version of.
Okay, let's move London to Tuesday and give Fatima to first chance to present her poster. Are you ready?
Yeah.
Okay. Please come.
You have how many minutes?
Well, the connection will be terminated in 40 minutes, but you can do much quicker.
In how many minutes? In 40? Oh, you have so 14 minutes.
Yes.
Wow. Okay.
Today is more than 2 hours.
How to make full screen? Anyone knows?
F5. Oh wait, you're.
And remove this.
You might have. Oh wait, like F11 or F12. I think we'll get rid of the.
Okay.
Japan.
Alright, I think I have to go.
And you can scroll over.
Especially you always go.
This is my last good reading. I know.
Oh, thank you for this service.
You can do one thing, Ben. Okay, you can take my key and then.
So don't forget us, come to visit us.
Oh, I will. And I'll see you guys for Boston too, so.
So this one is.
So you may approach and finger things
and
there.
if we need this view.
Okay, so
You believe?
Yeah, I'm not sure. This one
so here the research is about 2 silicon nanowires, theories of dynamics of 2 silicon nanowires, silicon 001 and silicon 111. So silicon nanowires are a unique class of nanomaterials because they have intrinsic properties such as one-dimensionality and high surface to volume ratio, and they are applicable in solar cells and lasers. So the electronic properties of silicon nanowires have been studied theoretically with different aspects, but there is a gap in studying for multiple K points. And for periodic solid, K dispersion is important. In this research, we studied electron dynamics for 2 different silicon nanowires for multiple K points. And here we can see the dispersion curve of 2 different nanowires. And we consider 4 different K points, and electron can travel from 1 K point to the same K point and 1 K point to the other K point, compared to the same path. And the method we used, we solved the 1 electron constant equation, and the solution of this one is this wave function. This wave function here, you can see it is dependent on K points. So using this equation, we can calculate the on-the-fly non-adiabatic couplings, and then we can calculate autocorrelation function using the this non-adiabatic couplings. Then we can calculate the rates of transitions from the Fourier transform of autocorrelation functions, and those rate of transitions are the component for calculating rate field tensor. And this is the time evolution of density matrix. The second term is the electronic energy dissipation. And here we can see the non-equilibrium charge distribution and the expected value of energy of a carrier. Carrier means paired electron. And we can use this equation to fit the relaxation rate. On the result sections, we can see homo-LUMO orbitals for 4 different K points for each model. And here we can see the transitions in these points for the indirect transitions and these for the direct transitions. And we fit using this equation. So for silicon 100, for each K points, for each K points there are 2 sections. First set of for first couple of initial excitations, energy, the rate follow energy gap law, and after that it follow inverse energy gap law.
Which figure are you showing?
Here.
So what does this figure show?
Relaxation rate.
How did you got them?
I didn't describe the MATLAB thing.
No, where the rates are coming from, and it looks like it's not rates; it is relaxation time. So which equation shows how you got this rates or times? But it shows only the expectation value of energy, and your rates are k. Where is this k? Where is the rate in this equation?
It's KE.
Okay, and how do you find it?
So we use the MATLAB code.
But which equation is encoded in MATLAB? Which equation is used to find the rate? Probably one needs to add it here. There is at least one equation is missing. So if
you can get it from this equation,
Hmm?
energy, like she already has equation for the change in energy with time, right?
yes,
You just take
But
a book of
but
it, solve
the-
it for tau, that's it, or for t.
it is what you wanted to tell, right? You understand?
Yeah. So this energy is function of time. Charge distribution is function of time and energy,
Mm-hmm.
and this is the energy of
Yes,
electron.
yes. But what should you do with the last equation to get the rate?
Oh, I think one more equation should be after this.
Yes. So which equation? What should be done to this equation to get the next one?
You need to solve this equation with respect to which variable?
So I need to take the logarithm and get this.
Yeah, you need to solve it for t, right?
Yes.
To find
Either
t,
take
you need to solve it for t.
either take
How do you do
logarithm or maybe integrate. When you integrate exponential, the rate comes to the front.
Yeah.
But
so
it
another
needs to be there.
one more equation should be.
So you do show a lot of points on your diagrams with the rates. Where these points are coming from?
For different states.
For different initial conditions, how do you choose initial conditions? Is it explained in the poster?
Yes, it's like says dir k equals 0 in dir k equals 0.
But
This is your initial conditions, right?
It's additional thing.
It's a key point.
So how do you choose initial conditions?
So in energy profile, final energy profile, all the states for 4 different K points are there, and we select the particular number of initial states as initial states.
But
At some specific energy?
So
yes,
we
but-
start from HOMO is energy, HOMO is 1, then below HOMO is 1 for holes. So LOMO is 1 and above LOMO
Oh.
is an
Okay, like you have after correlation function, right?
Mhm.
And it has so many indexes in this function, right? So which of these indexes stays for the state?
I and J.
ij?
Yep.
Okay.
or this pair of states, you probably need to I
Orbitals.
and K.
Together.
Yes.
Well, k stays for the k momentum, right?
So I didn't get answer to.
But it kind of relates to your question.
Okay.
So your after like because she's finding rates based on the after correlation function, and to this after correlation function, you really have to contribute only 2 states contributing, right?
Mm-hmm. Yeah.
So which ones? Home and Luma, or which states you really consider in there?
So one.
Or you really look all of them?
It might be it might be at same K points, two different states, or different K points, two different states.
But which pair of states are choosing? At some specific energy or
So let me be more detailed in the question. I see 2 possible answers. You systematically explore all possible excitation energies, just one by one, or you select optical transitions with largest oscillator strengths. You have so many points. How do you
Yeah, I
select?
selected just first 10 states.
So 10 lowest orbitals.
Yeah.
Okay, so you just systematically scan through possible excitations. Okay. And you are showing equation for n sub k, n prime, delta n, right?
Yep.
Third line from the bottom of your, yes. So what it is, and
This is equilibrium charge distribution.
but do you illustrate this equation by any figures?
I think for illustrating this one, we need green figure.
It would be really great.
which figure?
Explain which figure you want to add.
Green figure. There's a
So what is green figure?
So electron is the path of electron, how it is coming to the bed edge. So like
You will have energy on your y-axis and time on your x-axis, right?
this is rho plus 5. So this kind of figure to explain. I need to put here.
So how energy changes in time?
But But then there will be 10 figures like this.
Well,
right? For each
one can show one the most representative and tell that the rest look similar. So in your research, you were doing like 60 figures like this, and each figure results in one number. So each point on your on this diagram represents
one figure, the dynamics figure. Yeah.
Okay, so you explored large range of initial conditions.
Yeah.
And now you summarize. So can you explain what is the summary?
So for silicon,
You are the only participant in the conference.
For a couple of initial excitations, for all K points, almost all K points, we can see it follows the rate follows the energy gap law, and after.
What is energy gap law? Just help us to.
So energy gap law is electron comes to the band edge quickly when they have the relative energy is closer between the two states. And after those couple of first initial states.
So if the x-axis on your diagram has smaller value, then the time should be shorter.
Yeah.
So it is. It should be linearly growing line if it obeys gap law. Okay. And can you finger on which line are you explaining right now?
These lines.
So you split your energy range onto intervals, and on different intervals you have different trends.
Yeah.
Okay. So please keep explaining.
Yeah, and for the difference between the relaxation rates for these 3 K points, you can see the difference almost constant, and for the 0.5, they change linearly.
Wait. Difference between what and what?
Direct and indirect transition at different K points.
But so how let's think, focus. Look around. Did everyone understood the figures?
No way. You have too many data on that figure. No one will understand.
Point by your finger and tell which lines belong to direct and which lines to indirect.
So
explain what is direct, what is indirect.
These lines are indirect for indirect transitions, and those lines for direct transitions. These colors are.
Let's start from the beginning. I don't understand what does it mean dissipated energy. Dissipated energy to where? For what?
Okay, so if electron comes back to the band edge from the excited state, it dissipates energy, right?
So it's the energy difference between like the frontier and wherever it got excited.
Excited state and the low.
Okay, one person in the audience has understood. Good.
And this is just for electrons. You're not considering holes.
No.
And then what your vertical lines shows? Like you have vertical red, green, and
this I wanted to show the difference between direct and indirect transitions, because these transitions for indirect transitions means we include the electron transition from one K point to another K point.
So I think these lines, like your vertical lines, they're not based on any data.
No.
I would take them out because you kind of have a very distinct, like those which are direct looks like they're on the top, right? Those which are indirect, they're on the bottom.
Exactly.
So you already, and something is in between. I don't know, like this pink linear kind of curve.
You're talking about this or
this with points? No, with points. The slope, the line with slopes. Yeah.
Oh, this is for direct transition at K point 0.5.
Can you remind us what is direct and what is indirect, and why do you?
But I would suggest take out these vertical lines because they really not help. You have already too messy kind of figure, and putting extra is really not a good idea.
Okay.
If you want, you can probably circle it or something and call it direct, indirect. But because they are very distinct, I said like they kind of have much higher, much lower, right? So you can say those which in the top is a direct, this is which in the bottom is indirect. Okay. And those which is in between, like this pink shape, linearly increasing, yeah. You just say, oh, and this one, whatever it is, looks like it's also indirect, right? Like the pink one. It's indirect with some different K point or something. Direct, I don't know.
Indirect, direct at point K. Direct transitions at point K. Point 5 K point.
Well, again, your colors also very close for this pink. You have two pink colors, and
maybe
you
use
had to make them different.
dashes for direct and solid for
yeah, or dashes would be really very easy to distinguish.
You could do like solid and open figures too. That would be another.
Oh, this one, yeah.
What I did for distinguishing direct and indirect data, I used dark and light colors.
They're too close.
This could be logically right, but not.
And don't
visually
forget, when you print, like one thing which you see on a screen, when it's on a screen, and when you print it, the colors are really fade and they look different, right? And they like the difference which you clearly see on the screen is not seen when you look on a printed version.
And for your co-authors, some journals charge fines for color figures.
Yeah, the easiest way would be
things should be distinguishable in black and white.
Yeah, the easiest way would be, I think, London idea about having field stays for direct symbols, right? And exactly the same symbols, but not field, the empty ones, stay for the same K, but indirect or whatever. Up to you, which one is which one. But I think then the overall, except one, they're really very well distinct. And if you really put it in a different, you can stay with these colors, but you can really have this open versus, or how say, empty versus filled symbols. Then I think it would be very easy to follow the logic.
And still, I'm sorry, I'm returning back. Can you please give definition? What is direct and what is indirect in respect to non-radiative transitions?
In our previous research, what we did, we studied electron dynamics for direct transition. It means if you look at this figure, you can see the electron can transfer from this K point to the same K point at different states.
But what you are showing, Fatima, what you are showing is optically driven transition across the gap. But now you are describing only electrons, only cooling.
But the same for the internet.
Well, definition of direct is indirect is similar, but can you point transition would directly correspond to what you have computed?
Okay. Suppose this is, if I consider this, electron can come back here.
Okay.
This is direct transition. If electron goes there, that's indirect transition.
Okay, so it is change dynamics inside the conduction band with or without change of
K values.
Of momentum. Okay.
But you have how many? 0, 0.16, 0.33, 0.5. So 4 K points. When you say indirect, it goes from 0 to 0.16?
Or 0 to 0.
So there are 4 combinations. Yeah. You add, like you integrate over all these different Ks or what? Yeah. So like your indirect means you already
take into account all possible pathways.
But and this is might be very
and direct means you artificially disable pathways with change of K point.
Like if you integrate, then your indirect already includes actually 4 different passes, while your direct has only one pass. Like you have only one contribution between, like you have really these electronic levels. With indirect, you have 4. You have much denser electronic states. Which means this difference in your, rates is really just dictated by the point that you have 4 times more lines there for each electronic level pathways, yes.
That was my question, and that why you got a lower lifetime, smaller lifetime in case of indirect transition always?
Because there are more possible pathways to coming back to the band edge.
Then it shouldn't be normalizing that way?
But if you look really just 1 over 1, let's say, you look really separately, 0, 0 versus 0, 0, 5, who would be the winner?
0 means you mean K point?
Well, if you choose only one specific pathway between K points, like for your direct, you have only 0 to 0, for example, right? Then you compare the 0-0 transition, your data, with when you have just two K points, 0, in between 0 and 0.15 or 0.16 or whatever you have the next K point, right? And instead of add them all together, really kind of look on each of them separately.
Because if you look on the combination of indirect and direct, indirect combination is 4 times higher than direct combinations. So when you're considering this coupling, you are counting the 4 times different coupling than direct transition. Is it something like that?
Yeah. Yes.
So is that the reason because of you are getting the, lifetime is shorter in case of indirect transition?
It might be one of the reasons. To answer really, is it the reason or not?
So there
it's
are
probably better to separate them.
At least 2 reasons. First, indirect transitions do include direct transitions.
Indirect, they do.
Yes. Indirect include direct.
So it means they all. It's not indirect direct. It's completely all possible pathways.
Yes, what she calls indirect, it means both direct and indirect.
Which again, it means it's
predominant.
5 times.
You'll be quicker. So 5 times, but here is the logarithmic scale. It is not 5 times. It is like 40 times.
Okay. So
and another
why
is
not
that matrix elements for direct and indirect can be also drastically different, and maybe it's not humble 4 times. It's maybe like something more important.
Okay. So in that case, we can say the indirect situation is kind of overall situation, overall scenario.
It's all possible scenarios.
Exactly. Yes.
Maybe instead of direct, you can call direct and then all or something like this, right?
You will be in the acknowledgements.
That was actually, I was confused because I don't know any theory behind it, but I assume that direct transition should be faster compared to the indirect transitions. So,
if you consider only single kind of contribution.
So now it makes sense, okay.
But can you, this is not that you need to do it immediately, but in general, can you really separate it and really look on your dynamics, as I said, like for direct only, then indirect, but only between 2 K points?
Oh, like disable direct and keep only those that predominantly not conserving momentum.
Yes. And then really see which of them are faster, and maybe you will see that 0 to 0.16 would be much more predominant than 0 to 0.5, for example, right? So it gives you much more interesting kind of analysis in general, right? And then you can really talk about predominant, maybe possible that you will really see the dominant, pathway.
Okay. Which K point? For which K point?
Yeah, maybe there would be specific case of K points which really mainly contribute, really governs the dynamics. Or maybe they really equally contribute, I don't know. Maybe overall you will see that all 5 have pretty much the same contributions, the same weight of their contribution to these non-erratic couplings. Also possible.
Okay, now after we have somewhat idea what are direct and indirect, explain how do you compare them?
Compare.
Because point finger where are your direct and indirect, and how you try to summarize their difference.
So these are the indirect and these are the direct data points.
Okay, so direct takes much longer time on your time scale. And now you are trying to compare how much they are longer.
Yeah.
Okay, so what is your methodology? How you compare their values?
So I subtract the direct, indirect from direct one.
At which point? For which energy or for which K point?
For these 4 K points.
Okay.
And for these first 3 K points, the difference is pretty constant.
And you are showing that differences equals 5. What does 5 means? How to interpret this number 5? In which units? Does it have dimension or it is dimensionless?
No unit here.
No units, okay. But number 5, how to interpret it?
The slope. Not slope,
no.
the intercept.
Or just offset. But
The difference of offset.
is it natural logarithm or decimal logarithm?
It's
Is it like means 10 to the power 5 or e to the power 5?
Natural logarithm.
Okay. And what is e to the power 5 approximately? It's like 200?
It's like 300.
300? Okay. So number 5 means these rates are 300 times different?
This is too much. This can't be true.
Well, if there are no, is it?
I don't think so.
But please double check, and maybe
You
make.
have 2 orders of magnitude difference between these two kind of cases.
148.
Okay. So.
1 order of magnitude.
2 orders of magnitude difference.
2 orders of magnitude difference. So in other words, if your relaxation rates are predicted on the range of a few picoseconds, now you're predicting it on 100 picosecond range.
So even if it is not correct and an error will be found later, right now it is the best data you have. It is so provocative and so interesting, so you may add the third column and tell like it is 150 times quicker or slower, so that audience understands what you're talking about. And is this difference the same for each K point, or there are some trends?
Yeah, for 0.5 K points, the difference is linear. You can see a linear equation here.
Okay.
This one is the intercept and this is slope. And for this 111, we can see for these 2 K points, 0 and 0.5, the difference is linear, and for these 2 K points, the difference is constant. They are close.
So momentum is typically a vector with 3 components, and you given only one number. Why? It is a provocative and silly question, but you better answer it.
It's narrower, one directional.
Yeah.
It is confined in other 2 directions.
So in 2 directions it is a gamma point, and you change value of momentum only in one direction. Okay. What else?
I think it's done.
Huh?
It's almost done, right? So.
We are very close to the answer.
Well, then the conclusions, right?
Yeah, then conclusions we discussed maybe the conclusions. Yeah.
Maybe I missed that on the this question is like, since you consider 16 different coupling here, how did you normalize them finally?
Normalize. I didn't normalize.
Because the 16 different coupling is, you consider 16 different electron transition scenarios, right? Maybe.
Are they? Does one need to add them together or split? Have them consider them as equal probability and divide them by the number of channels?
I guess yeah, maybe that way it should be. Because probability is different in every case, so you are getting.
But if you have several, like if you have plastic container with water, if you do 16 calls, it will drip 16 times quicker. You do not need to normalize.
So, but you consider the one single
Well,
electron.
then take 1,000 K points, it would be 1,000 times quicker. Then you will have very different values comparing your experiment.
That's a good point.
Something is.
This is a good point.
Something is wrong here.
This is a good point.
Because in every coupling, that means one electron is giving a kind of probability of transition of one electron.
Yes.
So probably there, since adding together is kind of integration over K points.
You need to.
One needs to multiply by delta K, by the offset between nearest K points. And then by this multiplication, if you will have 1000 k points, each of them will be multiplied by 0.001, and it will be kind of normalization. So one needs to add multiplication on the offset between 2k points, which is like about 0.16 here. So the first and second are offset by 0.16. Next are offset by 0.17, and next two are offset by 0.17, right? In your first column of your table.
Yeah.
Good. Javet, you're for sure.
Put him as a cow. Not
Normal.
enough?
Normal. Keep trying. Keep trying. Normalize by multiplying with delta k. Good. And then it will be not as glowing difference, not two orders of magnitude. But
Just one order of magnitude.
Yes, which will be more trustable. Okay, good.
Wait, do you want to multiply by delta k, or would you want to divide by that?
Probably multiply, because you integrate. When you add together all channels.
But delta k is less than 1, right?
Yes.
Yeah.
Yes. Multiply each factor by small number, and then it will be.
It will be smaller.
Oh, I guess he is right. Then you need to divide by the whole
But it,
number.
like, it shouldn't change if it's smaller than 1 or bigger than 1, right? If you went bigger than 1, then you just
No.
everything
K
up.
changes from 0 to 0.5. It is already dimensionless.
Okay.
Right. Or divide by number.
I mean, multiplied by the delta k, and then whole number divided by the total
Number
k.
of k.
Will this delta k be constant as you keep increasing the number of k points in the calculation?
You can keep it as constant or not, right? Actually.
Well, it is
Yeah,
more
just
problem of not problem. but
Symmetry
aspect
of your
fun.
system probably is dictating this delta k. Actually, what's the reason that you were using this specific 4k points? Do you have any
Is there
special
one way?
ideas why this were choosing?
Yes,
Why
yes,
not
exactly.
taking 0.6
Actually,
instead of 0.5?
Yeah, I explained it in my last talk. You are not here, so I can explain it again. I calculated a dispersion curve for 16k points and for 4k points, and the shape of these states same. Like
The density of states. The shape of density of states stays the same.
4 points
So-
give you the representative figure shape of the overall.
So what are your conclusions?
my conclusion is
Everything has to be normalized.
so the indirect transition is quicker than direct transition.
Good conclusion. And probably if one
But
normalizes, it will
don't
stay.
call it indirect, call it all
All
possible
transitions.
transitions, right?
Yeah.
So to be kind
Direct plus indirect. Is it time
But there
for-
have any literature support from this to support these conclusions or anything?
Do we have
experimental?
actually rates, relaxation rates for experimental data for this type of system?
Or maybe similar things, kind of.
Well, in silicon rods, you cannot find the relaxation rates.
One probably can.
Yeah, I can.
Just to see again how close you are.
Is
At
it-
least, is it really?
Which one is more correct by order of magnitude?
Yeah. Is it on the picosecond range or hundreds picosecond range or tenths picosecond range? Right, something like this. On the other hand, they're probably thicker, right? You don't like it's 1 nanometer. How thick your layer, your nano, whatever you call it.
On your,
Nano-
on your first
nanowire.
figure, you have cross section. So what is the diameter?
What is the diameter of your nanowire? Around 1
And
nanometer or more or less?
7 angstrom.
Okay, so it's even less than 1 nanometer. It's very extremely small,
Very,
extremely
very
narrow.
tiny. So in addition, all observations can be affected by confinement.
Yeah.
Did you do any K-point sampling?
It's provocative question.
K-point sampling.
Because in your calculations, how big is your unit cell and so how many K-points you need to get the.
Oh, but this is, I think this is what she says, like if she takes only 4, it's already kind of showing the density of states for the entire system.
Her first figure is K-point sampling. It's like the check, would you agree that you are showing K-point sampling?
Well, this one is a 2 different system, right?
Yeah.
Yeah.
What is the difference between these two systems?
So it is cut in different directions, different plane.
Growth of nano rod
direction.
is different direction. So you should call it nanorod or nanowire?
Nanorod, nanowire.
Nanowire, because nanorod it would be confined and you have infinite, right?
Well, nanorod means you have very long. So you can find but not really affect.
On experiment they call nanorod if the length to diameter is about factor 10.
So you can already probably take it as.
But if it is longer, then it is nanowire.
Okay. But I think nanorods, you can find nanorods of about 1 nanometer in diameter.
Yes.
But for nanowires, usually it's much wide. It's maybe longer, but it's also much wider as well. So
Well, some papers from your reference list may have this data on relaxation rates.
So this normalization condition that Java mentioned is not in it.
No.
that's why they put it in
That's
the
why.
acknowledgements.
Yeah.
So
There are huge time difference, yeah. That's
how important is it? How much will it change?
It looks like it will change orders of magnitude. So
Well,
it's important.
If there are 4 key points, it means that each
16 different combinations.
so divide each rate by 16. So instead of 150, it will be like 10. In fact, one order of magnitude difference. So it's still it is important. It changes from 2 orders of magnitude to 1 order of magnitude difference.
Okay.
More questions? If no, let's thank Fatima once again. So we have agreed to postpone anyone in the waiting line to the next meeting on Tuesday. Okay, and Fatima, please collect whoever was doing comments and implement them over the poster.
Something. Are we done?
Yes, meeting is dismissed. Have a nice weekend.
And for the next week, those people who didn't answer, right? So please let us know so we know